shall we start by talking about the various kinds of numbers?
Yeah, that sounds like a good idea.
Okay.
So why don't we erase some of this?
I'll erase. Okay.
So when we talk about the various kinds of numbers, we can kind of formalize that definition with different sets of numbers.
Okay.
So a set is a collection of elements.
Yeah.
So when we talk about a set of numbers, it's just a set where each element would be some sort of number. So why don't we start off with the most basic definition, one that you and me learned in like junior kindergarten.
Okay.
So it'd be the natural numbers. So it's represented. Oh, there we go. That's an n. It's represented by an n with kind of an interesting script on the left-hand side.
I think. How is it?
Yeah, that looks better.
Yeah. So it's the normal capital N, but with the two vertical bars on each side.
Yes. Don't ask me why it's two vertical bars, but that's it.
Okay.
So when we think about the natural numbers, we're thinking 1, 2, 3, 4, and so on. Some people include 0 in there. Some people don't.
Right. So I think that's an important point to point out is that for natural numbers, there's disagreement, unfortunately, in the mathematical community about whether or not 0 should be included in the natural numbers. Some people say it's just the positive numbers. Some people say it's 0 and the positive numbers. Okay.
Yeah.
So those are the natural numbers.
So those are the natural numbers. So that's pretty standard.
Yeah.
Going on,
yeah.
So that's the most basic definition. Eventually you get to grade 3 math, right?
Yeah.
And you're talking about integers.
Yeah.
So integers being the natural numbers, but including positive and negative numbers.
Right.
So it's like a mirror image of each other, including both sets of elements. So that would be the integers.
Right.
And that's what I guess you use most of the time until you get to maybe high school or university level math, and then you run into some more interesting concepts of what a number is.
Right. Now, is integers, is that Z?
Yes, Z. Yes. With the double bar on the
diagonal.
Exactly.
Yes. Okay. So these are the natural numbers.
Yeah.
Yeah. Okay. So those are the natural numbers, and then these are the integers.
Yeah.
Okay. So, and I think it's important to point out the integers do include 0. Right?
Yes. The integers include 0 for sure. And I'd point out too, it's interesting because all of the little symbols we'll look at, it kind of makes sense. The Z. Why is it Z, right? It turns out there's it was German, and there's a Z in the German.
Okay, so we'll accept this. We'll accept this.
Accept it without proof. Okay. So we'll move on to the rational numbers.
Okay.
So the rational numbers are basically any numbers which can be a fraction of 2 integers. So let's maybe formalize that. So let's have Q. There we go. Okay, Q. It's got a little bar right there.
Okay, yeah.
Okay, so this would be, let's say, the set of all numbers. P over Q, so that's a fraction.
Yeah.
Or we'll say P is in Z. Say Q is in Z. And Q...
Right.
Q does not equal 0.
Right. So I think this is just a little too small.
Sorry.
If you could write those just a little bit bigger.
Okay, let's write that a little bit bigger then. There you go.
Thank you. Okay. So
there you go.
So the rational numbers are the set of fractions such that the numerator it could be an integer.
Yep.
And the denominator is an integer, but it cannot be 0, which of course we all understand because you can't divide by 0. That's undefined.
Right. Okay. And you can start thinking about the type of numbers that are in the rational numbers. So if P was equal 1, Q is equal to 1/2.
1/2.
That seems to make sense. Or if P was equal to 2, Q is equal to 1, that's just 2.
Right.
So the rational numbers, they include all of the integers.
Right.
And then they include some more numbers like fractions, because fractions aren't in integers.
Of course.
So
we'll just write these are the. Can you just write these are the rational numbers?
Yeah, I'll write it. Rational. Rational.
Excellent.
Rational numbers. There we go.
Okay. So we have the rational numbers, and of course we take the opposite of that, those would be the irrational numbers.
Irrational.
What are the irrational numbers?
So, and we'll look at this a little bit more later in the episode.
Yeah.
There are some numbers that you cannot represent as a fraction.
Uh-huh.
So some of these numbers include, as we'll see later, the square root of 2.
Uh-huh.
They also include pi. They also include e,
Yes.
which is like constant growth. It's
Yes.
related with that.
Yeah.
Another way to think about it is these are numbers that have an infinite decimal representation where there's no repeating decimal and there's no periodicity of the decimal.
Right.
So it doesn't go 1.13131313. You can basically prove that those numbers can be represented by a fraction. So pi, 3.1415, yada yada yada.
Right.
It never repeats. It doesn't repeat itself in a periodic or just a straight up way.
Right. So I think one good example is probably 1/3. Right. We know that this is equal to 0.3333.
Yep.
On and on and on. So even though there is an infinite decimal expansion, I'm sorry, I'm really bad at drawing threes today. This is terrible. Okay. So even though there's an infinite decimal expansion of this number, it repeats.
Yes.
So this is still a rational number.
Yes, right? That is correct.
Or if I believe 1/7 is equal to 0.142857, and then it just repeats like this, 142857.
Yes.
It keeps going like that. So even though this is an infinite decimal expansion, there is. Would this be a period? Is this the period?
That's it. Yeah, it periodically repeats itself, right?
Okay.
And the proof actually is pretty simple. You basically look at 1/7. Let's call it. Do you mind if I?
Go ahead.
So let's say a equals 1/7. Do you mind if we just erase that part right there?
Okay.
So equals, let's say, 0.14 2857 7, and then it repeats itself. So 157 repeating, and it's actually kind of interesting what you can do. What you can do is say, okay, well, if I multiply this number, so it'd be, let's like move the decimal, so it's 10, 100, 1,000, 10,000, 100,000, a million. So if I do, let's say, I just 1, 2, 3, 6. And I take a million A. I'm going to subtract A from it. And then you see what you have. You have this part of the number, but then you've lost the repeating decimal. So you get something along the line of 1, 4, 2, 8, 5, 7. All of a sudden, so this is 999,999.
Yeah.
A equals 142,857, and then you can just finish it off saying, A equals 1, 4.
And we'll just write a comma.
Let's put a comma just to make it
clear.
Clear.
Yeah. Okay. That's really neat. I hadn't thought about that, but that's a really cool way of showing this. Okay.
Right.
So these are the rational numbers.
These are the rational numbers.
And so sorry. So going back, I don't. Sorry, audience. I took David on a tangent here. Okay. So irrational numbers are numbers that you cannot represent by a fraction of integers.
Right.
Okay.
Yes. And we'll dive into you'd think, and this is part of the reason I find this so interesting. You'd think every number would be able to be represented by a fraction. That just seems to align with our natural understanding of what a number is. But we'll see in a bit that there are some numbers you can just prove this isn't the case.
Okay.
And probably it's worth mentioning the real numbers quickly, because that's what, when you're doing mathematics, usually you're using real numbers, and that is the union of all rational and irrational numbers.
Right. Okay.
So we'll see that later when we talk about bijections and whatnot.
Okay.
That's the real numbers.
Okay. So irrational numbers are numbers that you cannot represent by a fraction of integers.
Yep.
And real numbers are rational numbers or irrational numbers.
Yeah.
The union between those two sets of numbers.
The union between the two sets. Yeah.
Okay.